ANOVA, analysis of variance. This statistical technique is used to test if there are more than three groups, if they belong to the same population, or if there is a significant difference between those three groups. Yeah? So it uses an F-test statistic, and we will calculate multiple sample F to find out whether these groups are statistically different or they're statistically same. Yeah? So an example of this would be, let's say an educational institution, a college, is trying to find out effectiveness of different types of delivery of education material, lecturing that they used to do previously, how that is effective compared to using case methods like real life situations that we learn from, or flipped as well, where you have some asynchronous work at home, you can do some asynchronous reading, watching some recorded videos, and then coming to class, and the combination of various mechanisms. So there are various methods in which an educational system would want to try out and see whether it is actually effective. So, and effectiveness in this could be average scores. Yeah. So this is our dependent variable. We would want to check how these independent variables, lecturing, case methods, or even like flipped classroom, impacts the dependent variable. Yeah, so we have certain aspects of teaching. We want to check whether the dependent variable changes, whether these three groups are statistically similar or they are different. So likewise, you would have several ways in situations where you have more than two or three groups. More than three groups is where this is useful to check whether they are same or whether they are different. You might see different metrics that you would look at for dependent variable. In this case, I have seen average scores as one thing that the school might be interested in. The school also might be interested in like how much money these people make after going through these three different types of mechanisms of learning. How much salary, yeah, money in terms of salary that they make, or even like they want to find out if these three groups are so different in terms of age and population size. So knowing from this sample of delivery of lecturing for the students versus case method versus flip, and then inferring about population as to what could be going on, that's where ANOVA is helpful. Yeah. So we understood what we're trying to do, and we have a lot of this that's automatically calculated, but really understanding the intuition behind this and doing it once will really help us understand how to manually do this. There are tools and packages available to calculate the multiple sample F statistic and give us the p-value directly to make a decision. But it's equally important to know like what's really going on under the hood. Yeah. So there are three similar steps that we do. We've covered this in one sample t-test, two sample t-test. Similarly, for three or more samples, we would use ANOVA, which uses an F-test statistic. Yeah. So the first step is to choose a hypothesis. The null hypothesis in this case would be that the mean scores for all of these three groups, x1 bar, x2 bar, and x3 bar, are the same. Yeah. That these teaching styles have the same mean scores, no impact. Yeah. That's status quo. If we see that we see an alternate reality, wherein if we can negate the null hypothesis, we get something significant against the null hypothesis, then we would have an alternate hypothesis which says, hey, there is differences, that they are not equal in terms of their effectiveness on this dependent variable. Yeah. So that's our hypothesis step. Second step, we then calculate the multiple statistic F, multiple sample F statistic. Yeah. So for all of these three groups that we have, we calculate one number. That will tell us how rare or how similar or how dissimilar these groups are. So the way it does it, it looks at two different aspects. One is the mean variance between the groups, and the other is mean variance within the groups. Yeah. So multiple sample F is treatment mean square, which is like all the treatments, which is in this case lecturing is a treatment, case-based method is a treatment, flipped classroom is a treatment. So for all of those, we try to find out treatment mean square and divided by error mean square. So what is treatment mean square? Treatment mean square is um, TSS, yeah, which is what I'm going to call treatment mean square as treatment sum of squares divided by unique treatments. In this case, we have 3 unique treatments, so it's 3 minus 1. So treatment sum of squares. So what is treatment sum of squares? We look at that here. Yeah. So treatment sum of squares, which is TSS, which is the numerator, we find out using this one. But treatment sum of squares requires weighted average of sample means. So we first calculate weighted average sample mean to get this numerator, which goes into TMS, which is the numerator here. We first have to calculate weighted average sum of weighted average of sample means. Yeah. So weighted average of sample means is you look at how many items are in the first sample, N1, times the average of this first sample, average scores in this case, which is a dependent variable, plus N2 times average scores of the second sample. So you calculate the weighted average, right? And then divide it by the total number of samples in all of these 3 samples. So then we get the weighted average of the sample means. Once we get the weighted average of sample means, we can substitute this and get the treatment sum of squares. Treatment sum of squares is number of items in the first sample multiplied by average of the first sample minus weighted average of sample means squared plus N2 times x2 minus, this is the second sample for the third sample. So for each of these 3 samples, we calculate the treatment sum of squares. Yeah. So N1, number of items in the first sample, times square of average of the first sample minus weighted average of the sample mean. Similarly, we do that for the second sample, and we do that for the third sample. We do the 3 items, we get treatment mean square. Yeah. So because that's the numerator that's needed for treatment mean square, which is treatment sum of squares. So far we've done from TMS, we were able to calculate TMS, which is the numerator here, and for that we needed weighted average sum of weighted average of the sample mean, and we also needed the treatment sum of squares. Yeah. So having done these 3, we're able to calculate the numerator, which numerator, as I said, is the mean variance between the groups. Now we need to calculate the mean variance within the groups, which is the EMS. Yeah. So let's calculate that. Error mean of squares. Yeah. So error mean of squares would be error sum of squares divided by total number of items in each of these 3 samples minus unique treatment types. In this case is 3. So error sum of squares, so EMS depends on ESS. So ESS is like for every sample, you sum the difference of the sample, first item in the sample minus the average mean of that sample squared. So for every item you do this within this sample, you sum all of those squared, sum all of the squares of these differences, and then do that for all the 3 samples. You get ESS, yeah, which is error sum of squares. You substitute ESS here, you get EMS. You substitute EMS here, you get multiple sample F. Yeah. So once we do all of this, this is the key. Yeah. If we get the multiple sample F, that's it. Now we are able to represent both variation between these groups and variation within these groups in one number. That's very powerful, and that is this number here. Now if you want to find out what is the p-value of getting a multiple sample F statistic of this magnitude, we'll have to get degrees of freedom, which is needed to get like a billion such, let's say, samples of F distribution. From standard F distribution, if you want to get a billion such samples, we need degrees of freedom. So degrees of freedom in this F statistic, we would require degrees of freedom upper and degrees of freedom lower. Degrees of freedom upper is unique treatments, in this case 3 minus 1. Degrees of freedom lower is total number of samples, except items in all of our samples, minus unique treatments, which is 3. So we get df upper, df lower. We substitute that and into a standard F distribution, which requires how many samples you want, and we say, hey, I want a billion such standard values from F distribution with this degrees of freedom, which upper bound and lower bound here. Yeah. So when you do that, we'll get like we'll get like a graph that looks like this. Notice that it starts at 0. Yeah. It's not a typical bell shape. It starts at 0. And so then, now we know what we will get a number here. Let's say this number was somewhere around like 5.6 was our F statistic, multiple sample F. So then we know it's somewhere here. Yeah. From a billion sample, our multiple sample F is here. Yeah. So then what we do is we calculate the p-value. That's the last step, which is basically adding up all of the counting, all of the from all of the billion samples that we have here, which of them have a value greater than our multiple F statistic. And that proportion, that probability is the p-value. So let's say in this case the p-value was 0.023, which is like 2.3%. Yeah. So in this case it is significant. Yeah. When it is significant, what we do? When it is significant, we reject the null hypothesis. In the null hypothesis, we said all of these teaching styles are same. This is powerful. It's telling us, no, this is rare. We can reject the null hypothesis. That means there is a difference now between these groups in terms of effectiveness on this dependent variable of average scores. So what I also mentioned here was, let's say there are these 3 styles, yeah, lecturing, case-based, and flipped. We start to see that lecturing, we see mean variance within this group, right, is medium, yeah. This group has much higher variance, yeah, and then this third one has a much lower variance, yeah. But we see between groups there is a major difference, yeah. This has this mean, this green group of lecture style. We start to see case method with a test score of much higher, and this is somewhere in the middle, yeah. So we start to see between groups, this is the mean for this group, this is the mean for this group, this is the mean for this group. So we start to see between groups, we can visualize how test scores are different. Similarly, we could do this for any other dependent variable. That could be, we could do this for like not just test scores, but we could also do this for, let's say the age of the people enrolling in this, or it could also be the salary that they make. So there could be several such dependent variables that you could use to say, hey, what is the test score for this group, and is this significantly different, or are these sample, the information that I'm getting from this sample is telling me that these populations are very similar. In this case, we're going to reject the null hypothesis, meaning these teaching styles have significant differences in them. Yeah. So that's ANOVA, analysis of variance. We use this when you have more than 3 groups and you want to find out how similar these groups are or not. Yeah. Thanks.